So here, this lecture is about the secant method. This is a basic method for finding roots of a function when you just know that it's continuous. Let's take a look. So the idea here, it's similar to the method where we did the Newton's method, that were to approximate our function by a line. Here, though, instead of having one initial guess, we have two initial guesses called x1 and x2. We let the slope of our approximating line, our secant line, be equal to the f of x1 minus f of x0 over x1 minus x0. And so again, with our line here, this m is this m. We then, as we did before, say, well, where does this line intersect the x-axis, setting y equal to 0? We then solve, and we can then obtain that x2 is equal to x1 minus, the fraction f of x1 minus x0 over f of x1 minus f of x0. Okay, so we can put in the code for the algorithm. Again, it's similar to the algorithm for Newton's method, other than we have two seed values instead of just the one. We run through, we'll be putting our output in a list. Y0 is f of x0, y1 is f of x1, and again, we put through, if the absolute value of y naught is bigger than an absolute value of y1, we choose our x0 and x1 one way, and otherwise we flip it around. We let S be the ratio of the differences between the x's over the differences between the y's. Okay. Do some relabeling, do recalculation of the function, and then append our values to the list. Okay. And continue this way. When we go through this, we see that we do get within our initial tolerances on 5 iterations. So this appears to take a little bit longer to converge than Newton's method, but it will work with functions that aren't necessarily differentiable. And so here we come to our error analysis. And so I'm going to summarize here. You can follow through with the algebra, but this is just substitutions, okay? And at some point we do some factoring out, and we try to be a little clever. Again, giving us this equation here. Again, we apply Taylor's theorem. Okay. The first time expanding around x0, the f of x n. The next time f of xn plus 1. I said that wrong. We approximate the f of xn and f of xn1 using Taylor's theorem about the root. Okay. We using that f of r is equal to 0. This then reduces to these next statements. Okay. We then divide both sides, the top equation by E sub n, the next equation by e sub n plus 1. And we take the difference between these two and get something that's reasonably pretty over here. Doing since en minus 1 is the same as x sub n minus x sub n minus 1, we will be able to say that this ratio here on this side, or excuse me, right there, is approximately equal to this. Okay. Doing some more approximation, we get that this ratio is approximately equal to f double prime. Rolling this stuff back into this equation here, we will see that en plus 1 is approximately equal to 1 over f prime of r times f double prime of r times en minus 1. So some constant times this product of the en and en plus 1. Okay, now we suppose that we have this asymptotic relationship right here. Okay, we're going to want to find the values of a and alpha. Okay. Doing our algebra on this, doing our rewriting, we get it to here. Okay. Again, running down the math on it. Again, we're again being just a little sloppy, and the sloppiness is in terms of leaving out the language which justifies this, treating that squiggly equals like an equal sign. We roll this down to the algebra leads us to saying that a to the 1 plus 1 over alpha times c, absolute value of c to the negative 1, is approximately equal to absolute value of e sub n to the 1 plus 1 over alpha, as the left-hand side is a non-zero constant, and the e goes to 0 as e sub n goes to 0 as n goes to infinity. That exponent, right, has to be equal to okay. Well, the algebra leads us to this quadratic equation, which we are then able to solve, and in choosing the positive branch, it'll roll out a little more. And so again, we have our we obtain our numbers to get this asymptotic formula for convergence, and the point of all this is we don't have quadratic convergence. Newton's method is better, okay, but it's not just a whole lot better. If you're given a choice and you can, you use Newton's method. If you can't, there's no shame in using the secant method.